So welcome everyone for the talk. And to speak a little bit about myself, I'm a geologist by background, and my area of expertise used to be sequence stratigraphy, but now I dived into the beautiful world of geodynamics, and now I'm doing structural evolution of the Black Sea Basin using section computational models. So here there is this geology map of the Black Sea to give you an idea where it's located at. So it's right north of Turkey, and the main geological features surrounding it are the Pontide Mountain belt to the south, the Scythian platform and Ukrainian shield to the north, and Moesia to the northwest, I would say. Uh, so here you can see on the top picture, we are looking from the west towards east to the Black Sea Basin. Turkey is located to the south, and the lower image shows a schematic cross-section roughly cutting the Black Sea around here, and it's showing the oceanic crust, the volcanic arc, and the subduction that caused the Black Sea Basin to open. So here you can see the back arc rifting is associated with oceanic crust formation in both western and eastern parts, and I will be diving into that a little bit later. So the main debates around the Black Sea Basin was whether or not the basin was formed as a single basin or two separate basins, and the timing and duration of the opening event was discussed a lot as well. And we proposed a new method towards the solution of this problem, which is doing computational 2D and 3D models and using aspect code for this. So the steps that we followed when we were trying to build these models were first building a structural framework and base our computational models on this structural framework. And what we required for building the structural framework is a beautiful seismic data set with basin-wide coverage and adequate resolution as well, so that we can define the structural or tectonic regimes that cause the basin to open and evolve. For this purpose, we looked around a lot, but many of the data is proprietary because of these oil and gas search efforts in the Black Sea Basin. So what we could find during our search was this data set that has 24 cross-cutting seismic sections that are mostly previously interpreted by different authors. So we started from these seismic data sets. We uploaded them to Petrel, and we started interpreting them using our background knowledge and following the literature, and try to build a 3D fault network that will be a guide to us when we are building these section models in the future. So the workflow that we followed for this, again, as I said, we did a structural interpretation, including fault picking, defining fault relationships in 3D, and defining timing of these structural events, relative timing of these. And now we built some 2D section models. We picked one of those cross sections and built our computational model based on those. And in the future, the third part of my project will be building a 3D geodynamic model that will reflect how the basin opened as a whole. And I will be talking about this in a while. So the structural geology part of our study was the fault interpretations, as I mentioned. Here you can see some of the interpretations, reinterpretations, maybe I should say, that we made. The normal faults are shown in blue, and the reverse faults or thrusts are shown red. We did this all throughout the basin, not in only selected lines, so that we could create a 3D mesh that I will be showing you in a minute. And we also these are the strike slip events, and I will be diving into them in a minute too. And we focused on the tectonic inversion that was defined previously by some authors, but what they did was only defining this tectonic inversion at the edges of the basin, like Romanian shelf, Bulgarian shelf. They were all limited areas, but we extended these interpretations in all throughout the basin using these seismic data sets. And eventually we created a 3D network of normal and reverse faults and the strike slip faults that we defined. And I'll be showing them in detail in a minute too. So speaking about these normal and reverse faults, they have this layout like that. And here on the central part of these two fault systems, we recognize the formation of oceanic crust. And because of this, there's this regional high here called the Mid Black Sea Ridge. Many of the authors thought initially that the Black Sea was opened as two separate basins named Eastern and Western Black Sea. But when we were doing our research, following the literature, we realized that there's this beautiful analog model that was created by Stevenson and Shellard, and they decided to explain the opening event of the Black Sea Basin as one single basin with a hinge to the east and with a greater vector to the west, that greater movement to the west, that caused these irregular ridge and depression geometry. They didn't really focus on these strike slip fault systems in their studies, but considering that this is the basement, we can still see some disturbances on their grid that reflect these strike slip fault systems. But when we plotted our interpretations on their model, we realized that our strike slip fault network almost exactly matched with their strikes with the ridge and depression geometry that their analog model had. So we decided to go on with this in our third part of our study to create a 3D model, which I won't be showing today, unfortunately, because it's still in the making. But we decided to open the Black Sea as one basin with a hinge to the east in our computational 3D models. So during this time when we are building our 2D models, we focused mostly on the kinematics, as well as a little bit about the viscosity and plasticity of upper and lower crust as well. And before jumping into our model setup and my section models, I want to talk a little bit about these distinct episodes of rifting and following compressional tectonics. So as these authors put in the past, the Black Sea started with several stages of back arc rifting, driven by several stages of southward migrating subduction events. And then there's this tectonic inversion stage. And in the end, up today, there's this compressional tectonics forming the mountain belts surrounding the basin mostly. And we see their expressions as tectonic inversion within the basin that I just showed you. So in the first episode, from the literature, we thought that it's about 17 million years, and the different speeds that we tried came to a conclusion that it is 0.15 times 2, because the two parts of the Black Sea Basin move in northwest and southeast. So, and it's followed by 79 million years of extension at the speed, and the speeds are like this here again, and it's followed by 34 million years of compressional tectonics, which has the speed of 0.05 times 2 per year. Now I want to talk a little bit about my model setup. So our initial models, it was based on this BS 110 seismic line that we show here. And the thicknesses that we used were for upper crust 20 kilometers, for lower crust 10 kilometers, and for mantle lithosphere we went down to 100 kilometers depth and not anymore, because we didn't do that much of a deep model because we only had these seismics as our guides, right? So these thicknesses are coming from literature as well. And when we started doing our iterations for different extension rates, breakup initiation locations, and stages of extension and viscosity and plasticity, we ended up with a geometry like this. I know it's a very low resolution model, but remember, this is one of the initial models that we created, and I'll be showing a better one in a minute, right after this one stops. So again, this is only extensional phase, but we moved on and we extended our model to 500 kilometers, and we kept the depth constrained to 100 kilometers again. Didn't play with thicknesses. Again, upper crust is 20, lower crust is 10, and mantle lithosphere is another 70 kilometers to the depth. But we wanted to do this in order to be able to reflect the compressional tectonics that kick in the last 34 million years and the mountain formation on the northern and southern part of the Black Sea Basin. And we are hoping to see the tectonic inversion events that are mainly expressed at the edges of these shelf zones here. So to play this model that we created, this is one of our very recent models when we finalized, let's say, fine-tuned the kinematics and viscosity and plasticity values of the upper and lower crust. I will leave you with this beautiful rift, breakup initiation, and oceanic crust formation, and now the compressional tectonics kick in that forms the mountainous areas to the north and south. So the next stages of this project will be doing this to the western part of the Black Sea Basin too, and then fine-tune our 3D model and come up with better velocities and better understanding of how the Black Sea Basin was formed as one single basin. And thank you for listening to me. It was a rather short talk, and I'm open to any questions that you might have now.
Thanks very much, Arman. I open the floor to questions. If you just put your hand up or indicate in the chat that you would like to ask a question. Okay, no, this is a response from Jeffwa for the first question. Okay, I have a question about this this analog model you showed with this rotation, about the pole of rotation a little bit to the east looks very nice. I mean, is there any other evidence that this model is applicable? You know, like for example, in your seismic data, do you see significant along rift changes in the amount of extension that you'd expect from this kind of model, or any other kind of constraints on whether this model is correct or not?
Yeah, our biggest smoking gun was actually the strike slip fault systems in the center. And they didn't incorporate any more sedimentation in it. So we basically see the throw in the strike slip system in the sediments themselves. But when we look at them, we literally see some flower structure sort of figures. I mean, the resolutions are not great, but with my background working in the oil business and stuff, I am pretty certain that I saw all of these transpressional and transtensional little mini basins that are formed in the sedimentary section. But other than that, the asymmetrical shape of the basin is another clue for us to move forward with it. And I guess that's pretty much all. Yeah.
Okay, thanks. Good. So, Anne, you've got a question, so just feel free to ask it.
Thank you. This is super exciting. I look forward to see the 3D modeling as well. I was wondering, this is kind of a technical question, but when you showed the video of the compressional phase, it looks like you have something going on at the boundaries. Do you know what this is?
Yeah, so it is one thing. Okay, I'm gonna be explaining it. So the thing is that there should be continuous material feeding from the edges, but I couldn't get Aspect to do it for now, and all I have is just it just stretches the material at the edges instead of continuously feeding in the crust, upper crust, the lower crust material, and mantle lithosphere material. So that's why you see these weird shapes at the edges. But we are basically interested in this area so this is a very vertical exaggerated version of this. So the seismic line is roughly located here. It goes down to 12 to 15 kilometers to the depth. So we only have hard data for roughly this area. And we are not really interested in this, but we also wanted to see the mountain formation and stuff too. But to answer your question, that is formed because we couldn't get Aspect to continuously feed in material from northeast and southwest. That's how it formed. But again, it's not our focus of interest.
I see. So it's more like how you set your boundary conditions.
Yeah.
Okay. Well, I mean, we can talk about that maybe over email if you
Yeah, that would be
want.
very helpful. Yeah.
Yeah, sure. Thanks.
You're welcome.